automation using Python. Hello everyone, in this lesson we will be covering DevOps automation using Python. We'll talk about some basic or commonly used tools, how to use Python scripts to log in remotely or automate certain DevOps commands, and other related contents such as remote SSH monitoring, automated email, network ops, etc. Here are the main topics. First, I'll give an overview of Python scripts, how to use them for debugging and performance testing. The second part covers routine activities in DevOps automation, as well as some commonly used tools for this purpose. The third part is related to text processing, including regular expressions and file operations. Next, we'll learn about two commonly used automated DevOps tools, SaltStack and Ansible. The difference between the two is that SaltStack is typically used to manage a large number of machines, say in the thousands, while Ansible usually operates on a smaller scale, for example, when the managed machines number in the hundreds. After that, we'll talk a bit about socket programming, including Telnet and SSH remote monitoring. Finally, we'll learn about firewalls, root tables, root tracing, and mail processing in Python. Since we'll often encounter alarms during DevOps, related emails need to be automated. We can do this very easily using Python. Let's start with an overview of Python scripts. Why is Python a preferred scripting language for DevOps? It's because Python has several advantages. First of all, Python has a rich set of open-source libraries that can perform DevOps-related tasks. Most of the tools that we'll cover in the following slides are of this variety. It makes sense to take advantage of these libraries in the DevOps process. The second advantage is that developers can write fewer lines of code when using Python. A characteristic of the language is its conciseness. That is to say, we can use as little code as possible to achieve optimal results. The third advantage is that Python has extremely robust functionality. When it comes to database operations, file operations, big data processing, more complex mathematical calculations, and artificial intelligence, Python is often the preferred language utilized. It is capable of handling a wide variety of tasks. The last advantage is that Python is very readable because it is so close to the English language. For point of comparison, we will be learning about shell scripts in Linux a bit later. Compared to that, Python scripts are very refreshing to read, especially when we have a large amount of code. Shell script can seem very messy. In this slide, we can see some differences between Python and shell scripts. Python is a systematic scripting language, while shell scripts could be considered a collection of commands and logical comparison. In Linux, it's called a shell script. In Windows, it's called bat process files. These .bat files usually look very similar, typically consisting of some function and method sets, as well as some loops, logical comparisons, etc. Generally speaking, its functional space is not as complete as a language. Secondly, it's generally easier to write more complex DevOps scripts with greater functionality using Python. If you try to do the same using shell scripts, the complexity greatly increases. This is because the rich open-source libraries in Python provide many convenient commands that can be directly utilized, while shell scripts almost exclusively rely on locally written commands. Here is an example of using shell script to check whether two variables are equal. First, we have the variable assignment, then the comparison. This is the related syntax. Finally, we use echo to return some results. Let's get on the Alibaba Cloud machine to see what shell scripts are available for an intuitive experience. This is my ECS server on the Alibaba Cloud. It's CentOS 8. Let's take a look. I'm using two machines. Here's a shell script that I found. Should be AWK. Let me show it on the display. This is the first method, which sets a path and exports some command. The next method essentially packages the functionality of this Gawk shell command and exports it. Compared with the Python script that we've learned before, we can see that it's far less readable. This is the intuitive experience. Going back to the slides, let's talk about using Python scripts for debugging and performance testing. What is debugging? Well, it is the process of finding problems or bugs in the code and fixing them. Oftentimes, when problems occur, we require the code to provide some related information so that we can go about pinpointing the problem. There are several ways to do this in Python. One commonly used is print parentheses, which prints out some variable. This is relatively simple and convenient, but not very standardized. There is also logging, which is an open source library. It is more standardized and can be outputted. Scripts or programs generally using logging to output to log files. Here's the display format of the logger that I wrote. It outputs the time, which program, which line, what was the error, etc. The third is PDB. This is typically used when we are close to the vicinity of the bug and start a single step through the code. The fourth is the debugger function provided by the IDE development environment. PDB debugger we will talk about later with a related demo. Let's first take a look at a logging script that I wrote and get a feel for it. This is the logger that I wrote. We mentioned that Python has an open source library for logging, which we can encapsulate. For example, in my class, the log is divided into 5 levels: debug, info, warning, error, and critical error. When we initialize, the default level can be set, and the output format defined as such. For time, the format can be year, month, date, hour, minute, and second. There is some fixed information to be outputted. Here we are outputting to a log file with the default level set to debug. After that, I output some other information for testing purposes. Here, we can configure the code to output to different files at set time intervals. For example, today's info gets outputted to a file with today's date, and tomorrow is a new log file. This way, when we put log into standard DevOps scripts, it gets automatically outputted to different files. If we find out an error occurred on a particular day, we can simply look at the log for that day first. Back to the slides, let's talk about exception handling. An exception is a serious problem that occurs when a program is running. When the program encounters the problem, it will exit, which is a situation we don't want to see. With exceptions, the general approach is to catch and handle it so the program won't stop running. This is obviously a preferred outcome to the program crashing or exiting. The screenshot here illustrates an example. It is a relatively simple case, division by 0, which will cause an exception. If we don't catch and handle the exception, the program will exit. When we catch it using try, the program can continue to run. Let's take a look at the difference in the result of the execution in terms of the program crashing at the point of exception or continuing to run when we catch and handle it. This is a division function. Normally, when there are no exceptions, we would execute 5 divided by 2 and then the following line. The next part illustrates the code running into a problematic point, and we have not done exception handling. Here it will encounter the exception, and as I've said before, the program will crash and exist without completing the execution. Let's see the effects with the demo. Here's the result of 5 divided by 2, and the subsequent line is executed as well. After that, the program crashes due to the exception and produces some error messages. The line after that does not get executed. This is a rather serious problem. Our case is a relatively simple one, and other programs may be much more complicated. If we fail to discover an exception during testing and one is suddenly triggered because the user inputted some strange data, the program will crash, resulting in a poor user experience. Here we catch the exception with try and print this information. The program does not crash and it continues to execute, giving a better user experience. Instead of crashing, it promotes that the data entered is abnormal and asks the user to re-enter, etc. Let's go back to the demo. The first line executes, resulting in 2.5. When it hits the exception, the program doesn't crash but it continues to execute this line, which catches and handles the exception. This illustrates a basic but important concept of programming. Back to the slides, we've just covered exception handling. Let's continue with PDB debugging. When we have a large amount of code, to pinpoint a problem, we may need to use PDB to single step through the program. There are 3 ways to use PDB. I will introduce them in the slides first and then show a demo. The first is to enter the Python script environment and directly write the related code, such as import some class. Here we import PDB. We can execute pdb.run on one of the methods in test, which executes the code line by line to see if there is a problem and prints out the related info. These are the PDB commands, which I will explain a bit further in the demo. The second method is to run Python m PDB on the program itself, which will execute it line by line and promote you at each point whether or not to continue. The user can look for any problem points and debug them before running the next line. The third method is to put the PDB commands directly into the code. For example, import PDB in the original code and put a set_trace parenthesis in the division function. When the function gets called, it gives a reminder that we've entered PDB debugging and will need to enter continue to execute the next line. Those are the 3 debugging methods. Let's take a look at the effects in detail. I put the relevant PDB code here. Let's do some debugging. With method 1, first enter the script environment, then import our text program. Let's copy this code over. Inside the .run parenthesis is a string representing the method in test, which will get automatically parsed and called. At this point, it will promote you to enter a command. We can use H for help to see which commands are available. Here's the list, which contains all the commands as well as the abbreviations. For example, continuing the slides is to continue execution, but can be abbreviated to C. This is the result of 5 divided by 3. Let's execute another. Here we can catch and handle the exception, which returns the string that we specified. This is the first way to use PDB. Let's quit. The second method executes test.py directly through python-m PDB. When a function gets called, it will automatically promote you to enter a command, whether or not to continue running. This means to continue and we've finished executing. The first line is fine, and the second line contains an exception, but the entire program gets executed. This will run on a loop, so we use Q to exit. For the third method, let's try adding pdb.set_trace parenthesis in the script and execute it. Similarly, it will promote you when it reaches a function. The first 2.5 is correct. The second line triggers a division by 0, so it outputs the relevant error message. Here the program gets executed just once. That's a demo of the 3 ways PDB can be used. Back to the slides. Another way to debug is to use crash tracing or essentially path tracing. When problems occur during execution, this will keep track of the specific line and the libraries that were called. Then print out all the relevant information. Let's run another demo. Here we use test 0, which happens to contain an error. This reflects all the codes in the program, which libraries were used, which line contains an error, etc. And that's tracing, which follows the path of execution. This slide covers code performance analysis. Sometimes we want to know the performance of the code or functions that we've written, which is basically how long it takes to run. Oftentimes, executing the code just once takes very little time and may be difficult to observe. We can instead run it multiple times, say 1,000 or 10,000 times, to get a better idea of the performance. To do this, we use timed parentheses. Here we have our code and related methods. In this slide, we have a simple timed parenthesis on the method in question, running it 10,000 times. The method is represented by a string in this case, but we can also call it directly. In the demo, we will illustrate both methods to test the performance. Let's go to an actual execution. Here's the code. We're using timed. In the first part, we directly write the function. The second part encapsulates it in a string to be called. Here we are calling the division function directly, because 5 is not divided by 3. With infinite decimal points, it is very time-consuming to run. The setup parameter serves to import the function from main. We go ahead and run it 100 times, so we see what the performance looks like. The second line uses the string representation. Here, it doesn't know whether the division is inexhaustible in the case of 5 divided by 3, or exhaustible, say, with 5 divided by 2. So the runtimes may be very different. Therefore, the first case should be more time-consuming than the second. Let's run the second one 100 times also and see what happens. We're using test 2. The difference is obvious. In both cases, we ran division 100 times. With 5 divided by 3, it takes 0.08 seconds. With the string representation, the time taken is 10 to the power minus 5, which is a difference of about 100 folds. So it's better to pass in some parameters to the method when we are using timed parentheses to more accurately reflect its efficiency or runtime. Now let's talk about some of the routine activities in DevOps automation, as well as commonly used tools. PSUtil is another useful Python library mainly used to collect information on Linux machines, including network stats, IP info, hard disk status, CPU status, process status, etc., which can then be put into the database for analysis. In routine DevOps, information such as process load status and memory status is collected regularly. Based on the info, certain alarms may be triggered and sent by email or warnings generated and output into logs or reports. But collecting the information is the first step. The installation is very simple. We'd use pip install PSUtil. After that, it can be used to generate statistics on the IPU, memory, disk, network, etc., all using Python scripts. Let's take a look at what these scripts look like and the results they produce. Here, we are using time to generate the year, month, day, hour, minute, and second, then printing it. The next session gathers CPU-related information. The library has a CPU count method, here being logical CPU, which is equivalent to the number of cores. Since we are on the early ECS, many of the CPUs are virtualized. So we set the logical parameter to false to represent the number of physical CPUs. The next part is the average CPU or core usage rate expressed in percentages. Then we have the CPU times and the stats, which we'll take a look at when we run this code. After that, we have a module that looks at memory stats, such as how much virtual memory is free. The calculation converts K to M to G, so it's returning how many gigabytes of free memory there are. The next line similarly returns the total memory in Gs. Here we are calculating a percentage of usage by first subtracting the amount of free memory from total memory to arrive at occupied memory, then dividing by total memory. After that, the data gets printed out. Here we have the overall memory stats, which we've calculated above, followed by swap memory stats. The next part covers disk-related stats. First, we have the overall and disk usage stats. Then we delve deeper into the partitions. Each I/O has several hard disks. So for each, we calculate the total used and free usage and print them out in the number of Gs. Finally, we have the disk I/O and per disk I/O stats. Here we have the network I/O and connection stats, followed by stats on the network card and information on the network card address. The I/O stats are converted into the number of MB for aesthetic purposes. The next module covers user information, how many users are logged in and their names, which we print out as well. Here we have the boot time, which tells us how long the server has been up and running. Next, we're retrieving a list of process IDs currently running on this machine in terms of specifiers such as process name and status. We'll need to use the following line and supply a process ID. Here, I've put in an arbitrary number 1058. We can see what information is provided on the process when we run the code. Let's go ahead and do that on the ECS server. This is an Alibaba Cloud ECS server. Let's upload the code and run it. Looks like I haven't installed PSSoto yet on this machine. We go ahead and do that as we mentioned in the slides. Then run the code and see what it produces. First, we have the date and time information. Then comes the CPU info. We can see there are 2 logical CPUs or 2 cores, and 1 physical CPU. The usage rate is very low. In fact, close to 0. Here we can see stats on user time, system time, idle time, I/O wait time, etc. Then we have the CPU status info, including the number of CPU cores switches, number of interrupts, number of soft interrupts, etc. In terms of memory, we see the total memory is 7.4 G with this much free and a usage rate of 9%. Next is virtual memory stats, total and available, with a usage rate of 5.9%. These 2 sets of stats are a bit different. Perhaps they were calculated using different methods. Here we have the swap method stats. For disks, it's showing that there is 1 hard disk Vidal1 mounted under the root directory on our cloud server with this file system type. Here is its size. How much is free with a usage rate of 7%? It should be 40 G based on the code, but maybe it's calculated differently. We can try to print out O.total as well and see where the difference occurs. Let's make the changes and take another look. There was an error stating that process 1058 does not exist. Let's choose a random one from the list since it's different for each machine. we go with 1558. Write it in the code and upload the file. Here we need to convert this to stir. Let's run the code again and go back to the disk section here. We see the stats from the two methods are different. That is to say, the stats obtained by disk_usage parentheses here is different from the partition stats here. The partition stats show just a 3G, but disk usage is showing a total of 40G. With this much free and a usage rate of 7%, so the two are different somehow. For disk I/O, it shows the read and write count and the respective number of bytes. Moving on to network, we see that there is a lot of information, which should be the same as the data obtained from running ifconfig in Linux. It includes how many bytes are sent, how many bytes are received, how many packets are received, errors, etc. There's also information on the specific network card with all the relevant addresses, except the display is not formatted properly, so it's a bit difficult to read. Anyways, all the info is here. We can clean it up if we choose. Next, we have user information. It's showing just one root user. Here's the IP to which the user is collecting from the terminal, the server start time, and a PID. Again, we just have one root user. The ECS start time is June 10th. Here are all the process ID numbers. The one we choose was 1558 in the code, and here's its information. The name is Ali Hips, the status is sleeping, and the start time is this time. So that's all the information obtained from this script. As we saw before, there's a discrepancy between the disk usage and partition data. Let's go back to the slides. We just saw the script used to obtain server-host exchange info in Linux. We can do the same in Windows using the WMI module, which contains info on the OS, CPU, disk, network, etc. We can also try to save the result to a CSV file, similar to Excel. Let's go back to the machine and look at the actual code. Here it is. I've generally organized the code based on functions. First, we need to import the WMI, sys, time, CSV, and codec libraries. Then we instantiate and assign a WMI object and use the following functions to retrieve various information. For example, the first function retrieves and points out the system-related information including the OS version, the system build number, the OS architecture, and the number of processes. There are many such methods. Here I'm getting the OS type and manufacturer. The next part looks at the number of the processor and the memory capacity. After that is CPU usage. When did it start running and for how long? Here, I'm storing info on process impact on CPU usage in a CSV file. The script will run continuously storing CPU usage info in this file. In practice, if some abnormality occurs, say CPU usage becomes too high, an alarm will be generated. Next is information related to the network card. First, access the network card and retrieve info on the MAC address, model, and name. Then check to see if there is an IP address. If so, the corresponding address and the net mask are obtained. If not, As in the case of virtual network cards, just leave them empty. For disk, we retrieve the logical disks. See how many there are and what their usages look like. Finally, I can each function and display the results with a separator. Let's run the code and see what it produces. As I mentioned before, the code will run continuously, printing out the CPU usage and writing it to the CSV file. Let's allow this to run a few times before turning it off. After that, we'll take a look at the output. Because there's a lot of content, we'll just pick a few key ones to look at. For the OS instance, I've listed out all the related information. There's quite a lot, but the ones relevant to us are at the bottom. Here's the OS version, which is the 2019 data center version of Microsoft's Windows Server. The build number is this. The architecture is 64-bit. The number of possible processes is now 120. The type is Alibaba Cloud ECS. The manufacturer is Alibaba Cloud. The CPU architecture is Intel Xeon Platinum. The specific processor is 64-bit. The architecture is 9 of the Intel 64 family. And that's the complete set of info on the CPU. Here it's showing there's about 8 GB of memory. For disk, there is assigned the complete set of related data. We see the bytes per sector is 512. The model is Red Hat SCSI disk device. Here is the signature. The size is about 40 GB. The status is OK, etc. The next part is the network information. Here are the IP and the MAC addresses, which are significant. There might be only one network card on this machine because it is on the ECS server. Finally, the CPU usage info will be saved here. Let's look at the format. It should be cumulative. Here are the CPU usage stats. The time is this. CPU is CPU 0. If there are multiple CPUs, they will be listed 0, 1, 2, 3, along with the usage rate. It all gets saved to this file. And that's all the info obtained by the script in Windows. Back to the slides. We just talked about collecting system info in Windows. We may also want to utilize another functionality, which is to log in to the server using a script and perform some operations. Once we log in, we may want to use PS to look at process info. It's for directory or file info, even DF for disk usage info. Or we may wish to directly execute commands from a program or script, which would require a more powerful module. Here, we will look at such a module called Paramiko, which has a lot of the functionality that we need. I will talk about them here and then we will run some related code. With this module, we can remote log in with the username and password or user key. The key is an encrypted string mat file. We will take a look at an example later. But basically, it allows you to log in without using the username and password, just to carry the file. There are also several ways to connect. One is to use the transport instance. Another is connecting using an SSH client. Finally, we can use an SFTP client to download from and upload to the remote server. And that's a list of the functionalities. Let's look at the actual code. Here's the test or demo code for Paramiko. First, we need to import the library. We just mentioned that there are several possible ways to connect. We can choose to use an SSH client or a transport instance. We can log in either a username and a password or a key. Anyhow, let's change some of these parameters and connect to this server. The username of the server is, the password is. After logging in, we execute the command is1. So for this first part, we create the client and set its parameters default. Here's the IP address of the connection, the username, and the password. Once we connect, we execute the command is1, print out the relevant results, and close the connection. The second method is to connect through transport. The password is the same for both. The command executed is also is1. We printed out the results, close the connection, and we are done. Those were two ways to log in using username and password. Now we do so using a key. Let's see where the key is. It's here. Let's format it like this. We then create a client and set the policy. With this, we need another server. The username is root and the P key is private, and we should be logged on. After that, the way to interact is by entering command, which is passed on to the other end. The result is outputted and printed out, and the connection is closed. We've just seen how to connect using two types of clients. Let's run the code and see what happens. We need to install the package first. It's done installing. Let's input a command. Both of the output results are 0, which doesn't tell us anything. So let's change the command to df and look at hard disk info. Remember, we have two different servers. One we logged in using username and password, and the other using a key. Let's look at the usage info to see if there is a difference. Here, the first two are the same server, just the two different connection methods, one using a client and the other transport. This is the other server. We can see the usage rates are different because the two machines are used differently. we have the info on how the hard disk in the file system is used in both cases. So that's the demo of running commands on the server through Paramiko. Back to the slides. Before that, I also have the script for file transfer through SFTP. First, we define the SSH connection class. Here's the initialization with the default parameters. Let me copy over the relevant parameters from the first file and put them here. We're using transport to connect. Once connected, we're mainly doing an upload and a download in the run method. We're uploading local file CPU info to the code directory. Test.cvs. That file doesn't exist in the directory. Let me change it to my test file to avoid naming conflicts. Let's see if there is a file called a test file. It's not there. So we create a new file and put in this word. Let's take a look again. When the script runs, it will prompt you to enter a command similar to the previous demo. But the main actions are uploading and downloading. We enter the same command, which is not particularly useful in this case. It's just illustrating the case when we log into the DevOps server and needing to upload or download data in addition to executing commands. This can all be done automatically using a script. We go ahead and execute the command. Since we didn't print any related information, we'll need to go into the directory and confirm if my test file is there with the specific content. Hello world. Hi. There it is. So the download was successful. What about the upload? Here should be a file with CPU-related info. Let's refresh and we can see the info from before. That shows the script works for both upload and download through SFTP, which is particularly useful. Back to the slides. We've just completed the demo on various functionalities of the Paramiko module, including login, command execution, and file download and upload. The next slide talks about executing external system commands such as is_i, ps, and df using Python scripts. To do so, we'd first need to import the subprocess library. Then, we could use the call method with the first parameter being the command to execute, and the second being the command parameter. In the next slide, we see that in addition to .call, we also have .run. The difference between the two is .call returns the execution results directly, while with .run, we can redirect the input and output to the pipeline. Then the data could be transferred to a file or database for further statistical analysis. Of course, we can choose to directly output as well. Let's take a look at the code and see how it works. The code is relatively simple. First, import a subprocess. For .call, we have the commands is_i and psu. There may not be any files for is_i to return, but never mind that. Next is .run, which directs the input and output to the pipeline. Finally, we print the results. Let's go back to the server and upload this file. We execute Python 3 iotest.py. Here are the .call results. For is_i, it lists the files in the directory, and for psu, we have the process-related information. After that is the .run output, the functionality of executing commands through a script and retrieving relevant data for further analysis or placement in a database will prove to be quite useful. Let's go back to the slides. The next part of the lesson covers text processing and regular expressions. Text processing is quite useful in daily DevOps work since oftentimes data in our logs and output are not in a format we wish to present or store, so we need to process the text first. For simple cases, we can just use various string functions. For more complicated ones, we'll need to use regular expressions. Let's take a look at both. For example, say we need to replace all the punctuation marks in a string. Punctuation marks include commas, periods, and question marks, and we wish to replace them with some other symbols. One way to do this is to put the symbols you wish to replace into a list and change them one by one. This is quite simple but useful. Another basic case may be that we wish to replace certain words in a string or delete some words or spaces from it. Let's take a look at some code and see how this can be done. Here we have the target string, in which we want to replace the periods, commas, exclamation marks, and question marks. How do we do that? Well, we first put the symbols to be replaced in a list, then create another list with the corresponding replacement symbols. Using a loop, we simply iterate the string and replace the symbols one by one, printing the result at the end. The second part illustrates string replacement. In this case, hello changed to hi. Deletion is equivalent to replacing a target string with an empty string. We can execute this code directly in Windows. Looks like I made a mistake here. This should be lowercase instead of uppercase. Run it again, and here are the results. First, we have the original string. After the punctuation marks are replaced, it looks like this. Finally, we can see hello is replaced with hi. And that's some simple text processing. Again, pretty useful. Let's talk about regular expressions now, which are very powerful. There are many expressions, and I've listed some commonly used ones here. You guys should take a close look at how they work, because they are powerful and commonly used. You can find most of them online. Be aware, though, that they may be incomplete or contain some omissions. You should test them out for yourselves. Let's quickly run through these. The asterisk replaces multiple symbols, and the question mark is just one symbol. Here means matching n times, which can either include 0 or not. Next is matching between n and m times. This represents the beginning of a string, and this the end. We would use this to qualify the beginning of a string must be a certain symbol, for example. These are some of the commonly used expressions. I encourage you guys to dig deeper or research a bit more on how they work since their functionality is quite extensive. The Python library for regular expressions is RE, which contains the functions on this slide. We'll demo how these work a bit later. Here we have compile, which compiles the regular expression pattern that can be used for matching or searching. Creating the pattern increases efficiency when we need to do the same task multiple times, because otherwise, the code will need to recompile with each iteration. The other functions are relatively easy to understand. Find all, search, match, etc. Split breaks up the string, sub takes a substring, and group segments the string based on the pattern provided. Let's go ahead and take a look at the code. Here I've included 3 functions. The first one is related to group. We have an ID number in the form of a long string with each position having some specific significance. In this case, the first 2 digits indicate the province, the next 4, the city in the province, and the 4 after that, the person's birth year, etc. We need to extract the relevant information all at once, which can be easily accomplished using the regular expression search. Here, each set of parentheses represents a piece of information we want to match, preceded by $P. Inside the angle brackets, we've defined a name. D means digit, and the number 2 means match the first 2 digits. Following that logic, we are taking the next 4 digits to represent the city, and the 4 digits after that, the birth year. S is the input string, which is the string above. Using this matching mechanism, we can extract the information related to each field. Finally, we print out the result of .group_dict parentheses. We'll see what it looks like later. But basically, it will show province is 32 and the city is 0219, etc. The next portion deals with matching mobile numbers. We know that mobile numbers follow certain patterns, and different countries have different standards. By setting the pattern, we can determine 4 set of strings, which are valid phone numbers and which are not. For example, in the first pattern here, the first digit is 1, followed by 3, 5, or 8, and 9 are the arbitrary digits for a total of 11 digits. That's one pattern. The next one starts with 147 followed by 8 digits, also 11 digits total. Similarly, the last one starts with 179. Let's compile it first, after which we can use it directly to match the mobile number here. If it is a valid number, we print it out. In the next part, we have a string with several numbers. To find which are valid, we use findAll parentheses S1 and print the matched results. Next, we are looking to determine whether or not these strings represent valid email addresses. For this, we use the pattern here. This is equivalent to a character. It can include horizontal lines, underscores, and dots. Both lower and uppercase letters are valid, as well as numbers 0 to 9. This is followed by the @ symbol and other characters or numbers and a dot, forming 2 to 3 segments. With that pattern, we can determine which are valid email addresses and which are not. The last one deals with URLs. For the URL pattern, it starts with HTTPS, followed by some upper and lowercase characters and a dot. Let's take a look at the results. First, we have the ID number match. Province is 32, city 0219, and the birth year 1991. Then we have the mobile number match. The first 183 is a valid mobile number according to our pattern. Within the string, only 183 and 138 are valid numbers. The others were not a match. For email, we see the first 2 are a match and the last one is not. Similarly, for URL, the Google addresses is a match and the second one is not a match. And that covers regular expressions, which are very powerful and useful for daily use. We just did a simple intro for some commonly used expressions, but you should study them in more detail. After regular expressions, let's talk about file operations. Some of the basic operations we can perform using Python scripts are creating or deleting a file or directory, checking to see if certain files or directories exist under the file system, checking the file size, inputting or outputting the file, etc. Those are some of the basic file operations. Let's take a look at the code. Here, I've commented out certain sections that produce a lot of output, which can make the results look a bit messy. You guys can try them out on your own time. The script is organized into several parts. The first is OS related, looking at the name of the operating system, the line separator, the text separator, and the environment variables. Some of the environment variables are quite useful, and you can try to configure them yourselves. For the directory section, we first look at the current directory and list out the contents of the home directory. After that, we make some determinations, such as whether this directory exists and whether or not it is a directory. We can check its absolute path, split the tag, and retrieve the base name and directory name. Walk takes a directory name and a file name, then traverses each path that it can reach the file and print out the results. The next few functions you guys can try out on your own. These include changing permissions on a file or directory, checking access permissions, rename, get the size, check whether the target is a file, etc. Let's go back to Linux. There were some minor issues with the code before. I've made the changes, so let's return it. Just to let you know the errors. One was an extra T in split text. The other was item in walk followed by a colon. Back to the output. We can see the OS is P06. The line separator should be carried to return, and the text separator is a slash. There are many environment variables. You can check for yourselves which ones are useful and even configure some of them. For directories, we see that we are currently in a home code directory. Lister shows that under home, there is just one code directory. The next section shows that the directory provided does exist, and it is indeed a directory. Then it shows the absolute path of the file. Split text separates the file extension from the rest of the directory and a file string. Here's the base name, which is just the file name and extension. After that is the directory name. os.walk looks at the path from home to code and lists the files along the path, akin to a traversal of sorts. That's all we have on file operations. Let's go back to the slides. Here, we introduce two very powerful tools for DevOps, Ansible and SaltStack. Both allow users to remote log into the server and run some commands for, say, statistical analysis. But their functionality is far more robust. They can also classify servers, for example, and perform powerful batch operations such as fetching data and executing commands. We'll cover a detailed example later. Both tools function similarly. One characteristic of Ansible is that it is lightweight. It does not need to install anything on the server. As long as you are able to remote log in, you can execute commands and perform operations. With the SaltStack, you must install the client on the monitored server. The client can be connected to perform related batch operations after simple configurations, such as the server IP address and the appropriate key. Another difference is scale. We mentioned before Ansible is suitable to manage units numbering in the hundreds, while with the SaltStack, the number is in the thousands. To install Ansible, we again use pip install. It also has a host configuration file, which we'll take a look at an example later. After the configuration is complete, we can use the command Ansible I for specific operations on the list of hosts. We can also group the hosts and run ops on a specific group. For example, here I'm running a ping-related operation on the group host test. The line after that is I related? The two subsequent lines perform timed background batch tasks on the web server, such as running this job every 10 minutes. These are just some examples. You guys can try it out on your own after learning the functionality. Let's run these example commands. These are the Ansible commands. For the host list, we grouped them into test, web server, database, and Nginx. The relevant fields are the same. First comes the host address, then the port, followed by the username and password. If you wish, you can assign it in a different name. Let's go run this on the server. We go ahead and switch to the server and upload the file. Let's check to see if Ansible is installed. It is. Let's execute the relevant commands, such as ping. Take a look at the results. This pinged 2 hosts. The first server is the one above. The second is this machine. So the ping was successful. Moving on to the second command, which is I on each host. There shouldn't be anything there since the home directory is empty. Looks like we need to install this SSH pass before we can remote log in. Let's do that using yum install. After installation, the 2 machines are connected. As expected, when we run I, we don't see anything. Let's change it to DFH to view the disk-related info. That's the info on this machine, followed by info on the server above. So that's some basic Ansible operations. Once you guys master these functions, I encourage you to study more powerful functionalities such as Playbook. For SaltStack, I did not prepare a code demo. As mentioned before, we first need to install SaltStack master, then a client on the monitored server. This is the installation command. Specifically, we install Salt Media on the client side and Salt Master on the server side. Both contain a configuration file, in which we need to set the appropriate IP address and key. Once it's started, the connection will be automatic. After that, we set them as system services, which can then be launched using these commands. To auto-launch the services, we need to run the enable command first. Once launched, we can execute commands by passing them as a string parameter to Salt. We can perform operations such as transfer files, etc. You guys can try this out on your own machine. As you can see, the SaltStack is very similar to Ansible, except that it's able to manage more machines because there is a client on the monitored server. The next section covers socket programming, particularly TCP, IP, and UDP. We'll illustrate TCP and UDP by using examples of sending messages, which will give you a good view of socket programming. Let's go back to the machine to take a look at the related code. TCP has both a server side and a client side, while with UDP there isn't such a clear distinction. The latter is similar to a mail system, which transmits in datagram mode. Let's take a look at the TCP server side. First, we import a socket as well as a thread. When the server receives a message from a client connection, the message gets processed in the thread while the server waits for other clients to connect. Take a look at the socket setup here, which creates a new socket with this address in stream mode. Stream mode means TCP, while message mode means UDP. Next, we set some options. One being IP address reuse. This is important because when we are testing the socket, we may open and close it multiple times. If the time in between is relatively short and we do not turn on IP address reuse, it will prompt you that the address or port is occupied and it cannot be used at this time. With this setting turned on, this is not an issue. This server binding 0.0.0.0 means that all addresses on the server are listing on port 9999. For example, 127.0.0.1 as well as all external and internal network addresses. This line sets the maximum number of current connections to 5. Within the true loop, we first print out that we are currently listening on the port. Receiving is in blocking mode. Once the connection is made, we can extract the socket and address, which we then place in the TCP thread as parameters. Finally, the thread starts. At this point, we return to the beginning of the loop and continue to monitor for client connection in blocking mode. With the thread code, we first print out the address of the connection. Then we send a welcome message to the client through the socket. After that is the message receiving loop, where we wait for 1 second before printing it out. We then append hello to the message before sending it back to the client and wait for further messages. At the end of the loop, the client closes the connection and we follow suit. Now let's look at the client, which looks much simpler. We also set up a TCP socket and configure the address to one of the Alibaba Cloud servers as well as set the port to 9999. The received information then gets printed. The message to be sent containing 3 names is placed in a list. The list along with an exit message is sent before the connection closes. These 2 files are already put on the server side. I've gone ahead and set one of the machines to be the server and the other the client. I ended up using internal network addresses here. Although I originally wanted to use external network addresses, however, external addresses had an access control issue that blocked the port, proving a bit too troublesome to work around. Within the internal network, there are no such security issues, so we can connect smoothly. Let's get the server side up and running first. That shows the TCP server is already in use on this port. Let's move on to the client side. First, the welcome message gets sent by the server, after which the client sends the 3 names. The server then adds hello to each and sends them back. B here signifies that the string is in byte format. On the server side, we can see that it received the 3 names. After this round, we close the connection, and that's the demo of TCP-related operations. Let's move on UDP. Here, we also import a socket. When a socket is created, there is a parameter socket diagram, which signifies its UDP, which similarly binds the UDP socket. After that, we print this line and wait to receive. For UDP, there isn't a distinction between client and server. Once we receive the message, it gets printed along with the address from which it was sent. We then wait for 1 second, append hello to the message, and send it back. Here, I converted the data to a string. So when we look at the result, we won't see the B in front. The other end is set up similarly. It also has a binding, since there isn't a distinction of client versus server. This end can also monitor for messages sent from the other end. In our case, this end initiates sending the message in a similar fashion to what we saw earlier with TCP. The message contains the same 3 words, except in the case of UDP. We must specify the destination address and port. After sending the message, we wait to receive before printing it out. Let's look at the results. We need to close the previous one first. With that, we're ready to receive on port 9998. On the other end, the port is 9997. There it is. Notice again the B is gone, since we did a format conversion. On the other end, we didn't do the conversion, so the destination is still there, meaning that it was transmitted in binary format. So that's all for TCP and UDP. Let's go back to the slides. Here we have firewall, routing table, and route tracing related operations. For these, we use a subprocess to call the corresponding system commands such as route or IP tables. Trace uses this command. Let's go straight to the code. Here we are printing the route. We can also add or delete. For commands related to route, you can check help to understand further. In terms of firewall, we're printing the IP tables as a list. You can also add to it with the corresponding command. Here, it's saying that the TCP connections on ports 22 and 80 are accepted. Let's run this code. We don't have subprocess installed yet, so go ahead and do that with yum install. The code earlier was missing and S is subprocess. I've added that, and let's take a look. Here's the route section. One is default and the other is the internal route of the Alibaba Cloud server. The firewall section is empty, probably because Ali ECS has a standard peripheral firewall. So eternally, there are no IP tables. If we wish to add one, we could do so using these commands. Again, there is a missing S here, and that's IP tables and routes. For trace route, we can use the package in Scapy. The access domain is Baidu, and the target domain split is blank. We use this particular port. For the trace route parameters, we add the domain, port, and the number of retires. This creates a graph of the route, which we'll take a look at later. It will then sleep for 1 second before continuing processing. Let's go run this. Many points along the route may not allow ping, so we may see a lot of asterisks in the trace route indicating those points. In terms of the graph, this machine is new, so it hasn't been installed yet. To install the graphics library, we need to use both yum install and pip3. After installation, we get this graph of the trace route. We can see the graph is very informative and easy to read. So that's trace route. Let's go back to the slide. We've covered everything on firewall, routing table, and a trace route. The last topic should be mail processing. Python can be used to set up auto email send and receive. We can break this down into 2 steps. The first is to log into a public email domain, which could be POP3 or IMAP. Nowadays, for security purposes, we must first configure the email account to receive external connections. The email provider will give you a one-time key akin to a password, which you will need for access. The corresponding Python library is divided into 3 modules. One is email, which is for parsing the email and the SMTP protocol. poplib and IMAPlib are for receiving emails. Of the two, CIS not often used now, while we see IMAP a lot more. SMTP is for sending emails, which is used universally. Let's take a look at the code. This is a sample Python code for sending and receiving emails. It looks like a lot of content, so let's focus on the useful ones. We start by importing the email parser, header decoder, URLs, etc. Base 64 is mainly used for encoding and decoding attachments. The next one deals with text transfer, and the one after getting the date and time. Finally, we're not using POP3, but IMAP, and we have SMTP as well to send emails. Let's go straight to the bottom, where we send and receive an email. Here's the function for sending. The first parameter is the form address using QQmail. The second is the receiving address, followed by the subject and the key from the sender account. We mentioned earlier that for security purposes, email providers will not directly use the account password as the send password, but rather a one-time key string. Again, this must be set up and activated ahead of time. You can't just use your account password. The rest is relatively simple. Just to put in the email address and a key. We also have a function for receiving emails. The emails have IDs assigned to them, so we just provide the corresponding ID to retrieve and display the appropriate one. Let's look at the send email function briefly. MSG is a text variable, which is HTML and UTF-8. From is the sender address, to is the receiver address, and then we have the subject. The next part deals with attachments and images, etc. You guys can test out multimedia-related operations on your own. The rest is connecting using SMTP. The QQ mailbox uses this port. It's SSL. Here we log in with the email address and key. Then send the email with the sender address, receiver address, and MSG formatted as a string. Receiving is very simple. We have the address and key. First, use IMAP to connect to QQ and log in. If this part is not okay, that means the login was not successful, so we return an error message. If successful, we print the relevant information. We go ahead and select the inbox and print again. Here, we select the email at index 0 and pause the contents. When I was testing the code earlier, I sent a test email, and there's the notification that it's being received. This is Python code mail test. We know that's the right email, so we don't need to check the contents. Here should be an attachment, which is a long base 64 string. Here should be the 0th mail group, in which I retrieved the next to last email and parsed it using the RFC 822 protocol, finally printing it out. This part deals with the subject and date, etc. Again, you can try it out on your own. Let's run this. I ran this before, but let's do it again to send the email. Scrolling up, we see the email was sent without any prompts. The email received the notification we just saw was from when I ran the test earlier. We'll also receive one after this, but we don't need to worry about that. For receiving emails, we see the login was successful and we were able to get into the inbox. The next to last email was sent from this address. Here's what the attachment looks like. Quite a lot of content. It looks like we paused the last 2 emails. Here's the other one. Below is the attachment of second email, which is even longer. The content is text in UTF-8 charset. Here's the subject, so that it covers the basics of sending and receiving emails. In the actual DevOps process, if you encounter some issues or problems, you can set up auto-emailing to the appropriate personnel to raise the alarm. With that, we conclude lesson 15. Thank you all.